Welcome back to another Explainer. Today, we're diving straight into our sources to unpack a real marvel of traditional mechanical engineering, the aneroid barometer. For centuries, sailors and meteorologists have relied on this tough, compact little device to figure out exactly what the atmosphere is up to. So we're going to decode exactly how it works using some really brilliant original schematics. So here's the big question. How on earth do we measure the invisible weight of the sky? It's kind of easy to forget, but we're basically walking around at the bottom of an ocean of air. Miles of atmosphere are stacked right on top of us, and all that air actually has physical weight. It's pressing down on everything. That pressure is constantly shifting, driving the weather. Measuring it out at sea relies on an incredible piece of engineering that translates that completely invisible weight into something we can literally see. Here's our agenda for today's Explainer. First, we'll meet the aneroid barometer, then peek inside the mechanical marvel. After that, reading and correcting errors, finding the perfect placement on board, and finally, predicting the weather ahead.
All right, part 1. Meet the aneroid barometer and its core principle.
Okay, before we even look at dials or numbers, we have to understand the heart of the machine, the single component that actually feels the air pressure changing. Check out this hand-drawn schematic from our source. Right in the middle, you'll see a box labeled partially evacuated drum, and attached to it is this thick, heavy piece labeled strong spring. This right here, this is the engine. Without this really delicate balance between a vacuum and spring tension, the whole system is just, well, a fancy paperweight. So, as the text explains, this partially evacuated drum, which is usually just called a capsule, has had almost all the air sucked right out of it. Because it's practically empty, the heavy air pressure from the outside room naturally wants to crush it flat. But it doesn't. And why? Because it's held open by that really strong spring on top. Being held in this state of super high tension makes the physical shape of the capsule incredibly sensitive to even the slightest change in outside air pressure. If that's a bit abstract, think about a plastic water bottle on an airplane. You know when you drink from it and cap it while you're cruising up at high altitude? As the plane descends, the cabin pressure increases and literally crunches the bottle inward. When the pressure drops again, it pops right back out. The capsule in our barometer is doing the exact same thing. Its physical shape actually alters, crunching in or puffing out, as the atmospheric pressure pushes against it.
Moving on to section 2. Inside the mechanical marvel, from squeeze to dial.
Now, the real magic is how we get from a tiny, microscopic squeeze on a little metal drum to a big, readable number swinging across the dial. The actual movement of the capsule is basically invisible to the naked eye, but there's a brilliantly designed step-by-step chain reaction. Atmospheric pressure changes, and the capsule deforms against the spring. That minute little movement is grabbed by a lever system. The lever essentially takes a tiny little push and swings it wider, magnifying the motion. Then, that tension is transferred by a very fine chain to the pointer spindle, pulling it and making the dial turn. It's a lot like the gears on your bicycle. Think about it. When you're in a high gear, a small, tight circle pedaled by your feet turns into a massive, super fast rotation of the back wheel. The barometer is doing exactly that. It's magnifying a barely visible mechanical crunch at the base into a sweeping, obvious movement of the pointer on the dial. Our source includes this fantastic cutaway view where you can really see it all come together. Down at the bottom is that corrugated vacuum chamber. Right above it is the lever system acting kind of like an arm, connected to this central spindle wrapped with that fine chain turning the pointer. All these delicate, ultra-precise pieces are bolted to a really solid backplate for stability, and then tucked safely behind a glass face. Section 3. Reading and correcting errors to get the true pressure. Okay, so we've got our reading, but here's the catch. The raw number on that dial isn't perfectly accurate for official logs until we apply a couple of specific corrections. Now, the source notes that most aneroid barometers are already compensated internally for temperature, which saves us some work, but you absolutely must manually correct for your height above sea level. Because air pressure decreases as you go higher up, you generally have to add about 1 millibar of pressure to your reading for every 10 meters of elevation you are above the sea. Let's look at a practical calculation from the source. For a ship's bridge sitting 38 meters above the water. First, take your raw barometer reading. Let's say 1,010.5 millibars. Next, calculate your height error. 38 divided by 10 gives us a 3.8 millibar addition. Finally, add your instrument's specific index error, which in this case is plus 0.3. Stack all those together, and boom, Your true corrected sea level pressure is 1,014.6 millibars. If you're not a fan of the math, just think of these corrections as zeroing out your equipment, like zeroing a bathroom scale before you step on, or adjusting a baking recipe because you live in a high-altitude place like Denver. You're just standardizing the reading so that no matter how high up your ship's bridge happens to be, your weather reports are speaking the exact same language as every other ship out there on the ocean. Which brings us to Section 4, Perfect Placement on Board, Finding the Ideal Spot. So a ship is a pretty chaotic environment, right? It's moving, vibrating, drafty. Placing a delicate instrument in that environment requires some serious thought. Our source manual gives strict rules for this. The barometer must be mounted vertically at eye level. Crucially, it needs to be as close to the ship's centerline as possible to minimize wild physical swings when the ship is rolling in heavy seas. And keeping it well away from drafts, sudden temperature changes, and vibrations keeps that super-sensitive internal index from shifting around accidentally. Honestly, a great way to think about it is treating your barometer like a really expensive, delicate houseplant. You wouldn't stick a fragile fern right next to a blasting AC vent or on top of a vibrating washing machine, right? You've got to treat this robust yet sensitive instrument with this same level of care so the fine internal chain doesn't jump or stick. But look, even with perfect placement, mechanical parts aren't flawless. The manual has this wonderfully analog instruction. Before you read it, give the glass face a little tap. Since the internal parts rely on tiny levers and a fine chain, friction can sometimes cause them to hang up just a bit. A gentle tap frees it all up, making sure the pointer drops into the absolute most current position. Oh, and always read it straight on at eye level. You definitely don't want a parallax error messing up your reading just because you looked at it from a weird angle.
And finally, Section 5, Predicting the Weather Ahead by Tracking Barometric Tendency.
Knowing the pressure right this second is great, but tracking how it changes over time, that's the real secret to predicting the weather. This change is called barometric tendency. Now, if you don't have an automated barograph charting this on paper, you can track it yourself. The barometer actually has a fixed pointer on the glass. At, say, 00 UTC, you manually align that fixed pointer right over the dial pointer. 3 hours later, you check back. If the dial moved right, pressure is rising. Moved left, it's falling. Note the change, realign, and repeat. And hey, if you see that pressure falling rapidly, you better believe a storm is brewing. It is genuinely amazing just how much predictive power is packed into this one compact instrument. Just a simple vacuum capsule, some clever levers, and a bit of careful observation, and we can translate the invisible weight of the sky into a forecast you can literally bet your ship on. So next time the wind picks up, you have to ask yourself, what exactly is the pressure doing right now? And what storm might your barometer be silently predicting? Thanks for tuning into this explainer, and we'll catch you on the next one.
If you are a deck cadet or preparing for maritime exams, subscribe to Deck Cadet Academy for more simple COLREG, navigation, and seamanship lessons.